Reflections. The Computational Universe. Excerpts from How We Became Posthuman, Virtual Bodies in Cybernetics, Literature, and Informatics by Katherine Hayles.
Caught in the dark, trapped in the chasms of your mind, looking for wholeness, yet narrowed by ignorance. You lack Cybernetics, the science of cycles. Cybernetics is hard to understand. It explains complexity and wholeness, an insight to free you from darkness, carry you into the daylight of a purer reason.
Let us start our tour of the computational universe at the most basic level, the level that underlies all life forms, indeed all matter and energy. The units that compose this level are cellular automata. From their simple on-off functioning, everything else is built up. Cellular automata were first proposed by John von Neumann in his search to describe self-reproducing automata. Influenced by Warren McCulloch and Walter Pitt's work on the on-off functioning of the neural system, von Neumann used the McCulloch-Pitts neuron as a model for computers, inventing switching devices that could perform the same kind of logical functions that McCulloch had outlined for neurons. Von Neumann also proposed that the neural system could be treated as a Turing machine. Biology thus provided him with clues to build computers, and computers provided clues for theoretical biology. To extend the analogy between biological organism and machine, he imagined a giant automaton that could perform the essential biological function of self-reproduction. Stanislaw Alam, a Polish mathematician who worked with von Neumann at Los Alamos during World War II, suggested to von Neumann that he could achieve the same result by abstracting the automaton into a grid of cells. Thus, von Neumann reduced the massive and resistant materiality of this self-reproducing automaton as he had originally envisioned it, to undifferentiated cells with bodies so transparent that they were constituted as squares, marked off on graph paper and later as pixels on computer screens. Each cellular automaton, or CA, functions as a simple finite state machine, with its state determined solely by its initial condition, on or off, by rules telling it how to operate, and by the state of its neighbors at each moment. For example, the rule for one group of CAs might state, on if two neighbors are on, otherwise off. Each cell checks on the state of its neighbors and updates its state in accordance with its rules at the same time that the neighboring cells also update their states. In this way, the grid of cells goes through one generation after another in a succession of states that, on a computer, can easily stretch to hundreds of thousands of generations. Extremely complex patterns can build up, emerging spontaneously from interactions between the CAs. Programmed into a computer and displayed on the screen, CAs give the uncanny impression of being alive. Some patterns spread until they look like the designs of intricate oriental rugs, others float across the screen like gliders, and still others flourish only to die out within a few hundred generations. Looking at the emergence of complex dynamical patterns from these simple components, more than one researcher has had the intuition that such a system can explain the growth and decay of patterns in the natural world. Edward Fredkin took this insight further, seeing in cellular automata the foundational structure from which everything in the universe is built up. How does this building up occur? In the computational universe, the question can be rephrased by asking how higher-level computations can emerge spontaneously from the underlying structure of cellular automata. Langton has done pioneering work analyzing the conditions under which cellular automata can support the fundamental operations of computation, which he analyzes as requiring the transfer, storage, and modification of information. His research indicates that computation is most likely to arise at the boundary between ordered structures and chaos areas. In an ordered area, the cells are tightly tied together through rules that make them extremely interdependent. It is precisely this interdependence that leads to order. But the tightly ordered structure also means that the cells as an aggregate will be unable to perform some of the essential tasks of higher level computation, particularly the transfer and modification of information. In a chaotic area, by contrast, the cells are relatively independent of one another. This independence is what makes them appear disordered. Although this state lends itself to information transfer and modification, here the storage of information is a problem because no pattern persists for long. Only in boundary areas between chaos and order is there the necessary innovation, replication tension, that allows patterns to build up, modify, and travel over long distances without dying out. These results are strikingly similar to those discovered by Stuart Kauffman in his work on the origins of life. Kauffman was McCulloch's last protege. In several interviews, McCulloch said that he regarded Kauffman as his most important collaborator since Pitts. Kauffman argues that natural selection alone is not enough to explain the relatively short time scale on which life arose. Some other ordering principle is necessary, which he locates in the ability of complex systems spontaneously to self-organize. Calculating the conditions necessary for large molecules to organize spontaneously into the building blocks of life, he found that life is most likely to arise at the edge of chaos. This means that there is a striking correspondence between the conditions under which life is likely to emerge and those under which computation is likely to emerge, a convergence regarded by many researchers as an unmistakable sign that computation and life are linked at a deep level. In this view, humans are programs that run on the cosmic computer. When humans build intelligent computers to run AL programs, they replicate in another medium the same processes that brought themselves into being. An important reason why such connections can be made so easily between one level and another is that in the computational universe, everything is reducible, at some level, to information. Yet, among proponents of the computational universe, not everyone favors disembodiment, just as they did not in the Macy's conferences when the idea of information was being formulated. Consider, for example, the different approaches taken by Edward Fredkin in the new field of evolutionary psychology. When Fredkin asserts that we can never know the nature of the cosmic computer on which we run as programs, he puts the ultimate material embodiment out of our reach.
I would like to suggest is that if you imagine a world where you have quantized space and time, and and everything in it is an integer in a sense, it's quantized, not like continuous variables. You can emulate everything we know in physics. It's just that it's just like when you have water, it looks continuous to us, but then we discover it's made out of atoms. So if we have space and time and somewheres it's not continuous anymore, but it's made up of something like a cellular automata, that's just as reasonable as atomic theory in some sense.
How do you escape the sort of hierarchical idea that, all right, if there's a computational set of instructions that specifies a universe, a reality, this room, for instance, how do you get away from the hierarchical notion that, well, then this is an illusion, then somehow one is more real than the other? The instruction is the reality, the realization of the instruction, the video game is the illusion. How do you get away from that? Ed first and then Seth.
Okay.
Well, the more interesting aspect to that question is, who's the programmer and where's the computer?
That's the Catholic Church, for God's sake. I mean that's going back. Oh my God, that's Copernicus and Galileo
but
and.
the answer
operating
is
system is not Microsoft. So
the answer is the computer is somewhere else, someplace I call other, some other place. And the point is, if all this is some kind of informational process running in some machine, the machine is not in this universe. It's somewhere else, and this universe is a consequence of its running. And so that's just a bizarre kind of fact, but it solves one very difficult problem, the cosmogony problem, which is, how did the universe get started? And I've never seen anything more harebrained than the ideas that came up with the Big Bang starting as some kind of quantum mechanical, just nothing turning into something.
Well, then.
Okay, but the point is, this doesn't have to be a mystery that goes on and on and on, because the place where there's an interesting fact about computers, you can build a computer that could simulate this universe in another universe that had one dimension, or two, or three, or seven, or none. Okay, because computation is so general, it doesn't need 3 dimensions, it doesn't need our laws of physics, it doesn't need any of that.
All we as human beings will ever see are the informational forms of pure binary code that he calls cellular automata. By contrast, the field of evolutionary psychology seeks to locate modular computer programs in embodied human beings whose physical makeup is the result of hundreds of thousands of years of evolutionary processes. The agenda for this new field is set out by Jerome H. Barkaw, Leda Cosmides, and John Tooby in The Adapted Mind, Evolutionary Psychology and the Generation of Culture. They argue that the model or metaphor of computation provides the basis for a wholesale revision of what counts as human nature. They aim to overcome cultural anthropologists and others' objections to the idea of human nature by offering a more flexible version of how that nature is constituted. They argue that behavior can be modeled as modular computer programs running in the brain. The underlying structure of these programs is the result of thousands of years of evolutionary tinkering. Those adaptations that conferred superior reproductive fitness survived. Those that did not died out. The programs are structured to enable certain functionalities to exist in humans, and these functionalities are universally present in all humans. These functionalities, however, represent potentials rather than actualities. Just as the actual behavior of a computer program is determined by a constant underlying structure and varying inputs, so actual human behavior results from an interplay between the potential represented by their functionalities and the inputs provided by the environments. All normal human infants, for example, have the potential to learn language. If they are not exposed to language by a certain critical age, however, this potential disappears and they can never become linguistically competent. Although human behavior varies across a wide spectrum of actualization, it nevertheless has an underlying universal structure determined by evolutionary adaptations. Thus, a science of evolutionary psychology is possible, for the existence of a universal underlying structure guarantees the regularities that any science needs in order to formulate coherent and consistent knowledge. This cybernetic computer vision of human behavior leads to a very different account of human nature. Although the evolutionary programs that the brain computer runs do not lead to universal behavior, they are nevertheless rich with content. The potentials lie not just in the structure of the general machine, but, much more specifically, in the environmentally adaptive programs that proactively shape human responses. Thus, children are not merely capable of learning language. They actively want to learn language and will invent it among themselves if no one teaches them. Like Weiner's cybernetic machine, the cybernetic brain is responsive to the flow of events around it and is adaptive over an astonishingly diverse set of circumstances.
I took over where others left off and collected information and labeled this field Cybernetics. The name comes from the Greek word for steersman. Cybernetics, though, may not be at all simple to understand at first glance.
The fact that only the intelligent machine is seen to be light enough on its feet to do justice to human variability in a measure of just how much our vision of machines has changed since the Industrial Revolution.
Amika, wake up.
What? Oh, it's you. Why are you waking me up? It better be important.
It is. I have a surprise for you.
A surprise? What is it? I can't wait.
I got you a cookie.
A cookie? But I can't eat cookies. I can't eat cookies.
Amika, cheer up. It's an internet cookie.
This is the worst joke I ever heard.
It will now perhaps be clear why the most prized functionality is the ability to process information. For in the computational universe, information is king. Luke Steels, an artificial life researcher, reascribes this value when he distinguishes between first-order emergence and second-order emergence. Surely it is no accident that the terminology here echoes the distinction between first-order cybernetics and second-order cybernetics, the grandparent and parent of artificial life. First-order emergence denotes any properties that are generated by interactions between components, that is, properties that emerge as a result of those interactions, in contrast to the properties inherent in the components themselves. Among all such emergent properties, second-order emergence grants special privilege to those that bestow additional functionality on the system, particularly the ability to process information. To create successful artificial life programs, it is not enough to create just any emergence. Rather, the programmer searches for a design that will lead to second-order emergence. Once second-order emergence is achieved, the organism has in effect evolved the capacity to evolve. Then evolution can really take off. Unlike humans, however, the machine programs are not hampered by the time restrictions imposed by biological evolution and physical maturation. They can run through hundreds of generations in a day, millions in a year. Until very recently, humans have been without peer in their ability to store, transmit, and manipulate information. Now they share that ability with intelligent machines. To foresee the future of this evolutionary path, we have only to ask which of these organisms, competing in many ways for the same evolutionary niche, has the information processing capability to evolve more quickly. This conclusion makes clear, I think, why the computational universe should not be accepted uncritically. If the name of the game is processing information, it is only a matter of time until intelligent machines replace us as our evolutionary heirs. Whether we decide to fight them or join them by becoming computers ourselves, the days of the human race are numbered. The problem here does not lie in the choice between these options. Rather, it lies in the framework constructed so as to make these options the only two available. The computational universe becomes dangerous when it goes from being a useful heuristic to an ideology that privileges information over everything else. As we have seen, information is a socially constructed concept. In addition to its currently accepted definition, it could have been and was given different definitions. Just because information has lost its body does not mean that humans and the world have lost theirs. The true King of all things, Christ Jesus, is and has always been the Word made flesh. His Word is the source of information, and he reveals the entirety of creation. Colossians 1:15-18 tells us, "He is the image of the invisible God, the firstborn over all creation. For by him all things were created that are in heaven and that are on earth, visible and invisible, whether thrones or dominions or principalities or powers. All things were created through him and for him. And he is before all things, and in him all things consist. And he is the head of the body, the church, who is the beginning, the firstborn from the dead, that in all things he may have the preeminence." Understanding information requires first knowing the Creator and reading His Word. Information in itself lacks majesty, prestige, and sovereignty. It cannot cast a shroud of grace over the human race. Jesus Christ reigns supreme over all information. Understanding this requires knowledge of Him and His living Word, the Bible.
I just love scanning for life forms. Life forms. You tiny little life forms. You precious little life forms. Where are you?